Dark matter might be the biggest thing in the universe that doesn't exist. And yet, without it, our best equations say entire galaxies should fly apart like sparks from a grinder. For nearly a century, something has been holding the cosmos together with an invisible grip. We've called that something dark matter. But what if the universe is not full of invisible stuff at all? And instead, it's our theory of gravity that's wrong. To understand how radical that is, imagine trying to fix a clock that runs slow. You can either add a hidden weight inside or admit that you misunderstood how gears work. Dark matter is the hidden weight. Modified gravity is the new gear idea. Both are trying to explain the same stubborn facts written across the sky. Astronomers first stumbled onto the dark matter problem in the 1930s. Fritz Zwicky studied a cluster of galaxies and found they were moving so fast the cluster should have blown apart in a few 100 million years. Yet it was clearly still there. The visible mass of the galaxies wasn't enough to provide the gravity needed to keep them bound. Decades later, Vera Rubin measured how fast stars orbit in spiral galaxies. According to Newton and Einstein, stars farther from the center should move more slowly, like outer planets in our solar system. Instead, Rubin found flat rotation curves. Stars in the outskirts were orbiting just as fast as stars near the middle. Something unseen was adding extra gravity, extending far beyond the visible disk. By the 1970s and 80s, evidence piled up. Galaxy clusters needed extra mass, individual galaxies needed extra mass. Even the way light from distant quasars was bent by gravity, gravitational lensing implied more mass than telescopes could see. The simplest explanation was, the universe is full of some new kind of matter that barely interacts with light, but does feel gravity. Dark matter. Cosmology embraced this idea. When you simulate the early universe with dark matter, tiny density fluctuations grow into a cosmic web of filaments and clusters that looks remarkably like what we observe in large galaxy surveys. Measurements of the cosmic microwave background, the afterglow of the Big Bang, show subtle temperature ripples that fit beautifully with a universe that's about 5% normal matter, 27% dark matter, and the rest dark energy. But here's the catch. Despite decades of searching, we have never directly detected a single dark matter particle. Experiments deep underground, in mountains, and in Antarctic ice have all looked for rare collisions between dark matter and normal atoms. They've seen nothing conclusive. Particle colliders like the Large Hadron Collider have smashed protons together at trillions of electron volts, hoping to create dark matter in the lab. Again, nothing we can confidently point to. So some physicists ask, what if the missing mass isn't missing at all? What if gravity itself behaves differently on galactic scales? In the 1980s, Mordechai Milgrom proposed modified Newtonian dynamics, or MOND. Instead of adding invisible matter, MOND tweaks Newton's second law at extremely low accelerations, about 1/10,000,000th of a meter per second squared. Below that threshold, gravity effectively becomes stronger than Newton predicts. This tiny change has a huge consequence. MOND can predict galaxy rotation curves from just the visible matter, often with astonishing accuracy. It naturally explains why so many galaxies, from dwarfs to giants, follow tight relationships between their visible mass and their rotation speeds. In a dark matter picture, those relations emerge from messy galaxy formation. In MOND, they fall straight out of the modified law. Other modified gravity ideas go further, trying to be fully relativistic, like Einstein's general relativity. Theories such as TeVS, FR gravity, and emergent gravity attempt to reproduce not just galaxy dynamics, but also gravitational lensing and the expansion history of the universe. Without invoking particle dark matter, they change how space-time curves, or how gravity propagates, especially over very large distances. So which picture works better? Invisible matter or new gravity? On the side of dark matter, we have the cosmic microwave background. Its detailed pattern of peaks and troughs, tiny variations in temperature and polarization across the sky, is exquisitely matched by models with cold dark matter. Modified gravity theories struggle to reproduce all those features simultaneously without quietly smuggling in something that behaves a lot like dark matter anyway. Then there's the bullet cluster, two galaxy clusters that have collided. X-ray observations show hot gas most of the normal matter lagging behind, slowed by friction. But gravitational lensing maps reveal that most of the mass has passed through, aligned with the galaxies, not the gas. The simplest reading is, there's a collisionless component, dark matter, that sails through the crash. Modified gravity can mimic some aspects, but it's an uphill battle. On the other hand, dark matter has its own headaches. Simulations with cold dark matter predict lots of small satellite galaxies around big galaxies like the Milky Way, more than we actually see. They also tend to produce dense cusps of dark matter in galactic centers, while observations often suggest flatter cores. Astrophysicists have proposed fixes. Maybe supernova explosions push matter around and reshape the dark halo. Or maybe dark matter particles interact weakly with each other, not just via gravity. Modified gravity shines at the scale of individual galaxies. It nails rotation curves with minimal free parameters and explains why low surface brightness galaxies still show strong gravitational effects. But when you zoom out to galaxy clusters and the entire universe, it often needs extra unseen components. Sterile neutrinos, or fields that effectively act like dark matter, which starts to look suspiciously like the thing it was trying to avoid. So what if dark matter really doesn't exist? Then we're looking at a profound revision of gravity itself. General relativity has passed every test in the solar system, and in binary pulsars, and even with gravitational waves, but all those tests probe relatively strong gravity. It's possible, though speculative, that on scales of tens of thousands of light years and beyond, gravity transitions into a different regime, emerging from deeper quantum or thermodynamic principles we don't yet grasp. In that world, the missing mass would be a mirage created by our incomplete equations. Galaxy rotation, lensing, and structure formation would all be telling us about new laws of nature, not new particles. The stakes are enormous. A correct modified gravity theory could unify gravity with quantum physics in unexpected ways. But it would also have to explain every success of dark matter cosmology, from the cosmic microwave background to the cosmic web, with equal or greater precision. For now, the universe hasn't chosen a side. Most cosmologists still bet on dark matter, partly because it fits so well with the Big Bang's afterglow and large-scale structure, and partly because particle physics offers plausible candidates, like WIMPs or axions. But the absence of direct detection keeps the door to radical ideas open. Each new galaxy survey, each more sensitive detector, is a vote in this cosmic election. The most important open question is brutally simple. Is gravity incomplete, or is there a whole dark sector of the universe we haven't touched yet? The answer will reshape not just our map of the cosmos, but our understanding of what matter and space even mean. Until then, every star you see is only a hint of the invisible story behind it. The story we're trying to read here on Terra Nova.